Imagine looking up at the night sky, seeing all those beautiful sparkling lights. Now, how many of those stars do you think are truly alone, just solitary wanderers in our vast galaxy?
Yeah, it's a good question to start with.
You might be surprised to learn it's far, far fewer than you think.
Precisely. The traditional image we have, a single star like our sun, that's actually less common than you'd expect, especially when you look at more massive stars.
Huh.
That surprising rarity of truly solitary stars is kind of the foundational idea we're exploring today.
Okay, so our deep dive today is all about stellar multiplicity, this incredibly compelling reality that stars often come in pairs, triples, or even larger complex groups.
hmm
It's like finding out the universe is full of bustling stellar families, not just, individual cosmic citizens.
That's a great way to put it. And our mission today is really to unpack a stack of groundbreaking research, especially really transformative findings coming from the Gaia mission.
Gaia, right. We hear so much about it.
Exactly. We'll explore how these multiple star systems form, what makes them tick, and why studying them is, frankly, profoundly important for understanding the cosmos itself.
We're going to dive into the surprisingly complex and sometimes, chaotic dance of these stellar families. It really makes you rethink how simple we once thought star systems were, doesn't it?
Absolutely. And what's truly fascinating here, I think, is that stellar multiplicity isn't the exception to star formation, it's practically the rule.
The rule. Wow.
Yeah, stars forming in multiples seems to be a ubiquitous outcome of how they come into being.
That's a huge claim. Stellar multiplicity as the rule. What makes it so fundamental to star formation? And maybe why was our traditional image of single stars so dominant for so long?
Well, this prevalence isn't just a cool fact, it's incredibly insightful. The frequency and the specific properties of these multiple star systems offer powerful clues, sort of like probes, into the star formation process itself.
Probes, how so?
They help us untangle the competing theories. Like, do stars emerge from collapsing, fragmented clouds, what we call turbulent core fragmentation?
Okay.
Or do they grow from swirling disks of gas and dust that become unstable and then fragment gravitationally unstable disk accretion? Observing these systems helps us tell the difference.
Got it. So studying the families tells us about the nursery they came from.
Exactly. And beyond just their formation, multiple systems offer so many other astrophysical insights. For instance, their precise masses, which we can get from their orbits, they underpin our fundamental estimates of stellar structure, age, and even composition.
Right, the basic building blocks of understanding stars.
Precisely. And here's where it gets really interesting. Their gravitational tugs can reveal the presence of truly rare unseen objects,
Like black holes.
like black holes and neutron stars, yeah, just by how their companions wobble or shift over time.
It's amazing.
It is. And the close interactions between components in these systems can also dramatically influence their entire evolutionary paths, leading to a huge variety of phenomena we simply wouldn't see in isolated stars. It adds layers and layers of complexity to stellar life cycles.
Which brings us to what seems like a simple question, but I guess it's actually incredibly complex. What fraction of stars in our galaxy are binary?
You'd think there'd be one clear answer, right? You would think. But not at all. That seemingly simple question is actually a complex puzzle. It reveals as much about our observational tools as it does about the stars themselves.
Okay.
Estimates range wildly, from as little as, say, 30–35% up to perhaps as high as 80%.
80%, that high.
Potentially, yeah. What we see depends entirely on how we look. When we talk about binary fraction, it's not a single number because we observe them in different ways.
Different methods.
Exactly. Visual binaries are those we can literally see as two distinct points of light through a telescope. Astrometric binaries are revealed by the slight wobble a star exhibits as an unseen companion tugs on it.
The wobble, right.
And spectroscopic binaries are detected by analyzing shifts in their light spectrum caused by orbital motion, the Doppler effect.
So it's about the method, but you also mentioned earlier something about their chemical makeup.
Yes, that's another layer. As recent Gaia results have shown, it even depends on a star's metallicity.
Which is?
That's the amount of elements heavier than hydrogen and helium it contains. Turns out, a star's fundamental chemical makeup can influence its likelihood of having companions. It's all interconnected.
Wow, that's, yeah, a much wider range and much more complicated than I would have ever guessed. Given the surprising prevalence of binaries, it naturally leads us to wonder, what about even more complex systems? Like triples or quadruples, are they just rare astronomical curiosities?
Not entirely rare, no. What's
Mhm.
fascinating here is that the likelihood of a star being in a binary or a multiple system actually increases as the component masses increase.
Ah, so bigger stars more social.
Generally speaking, yeah, bigger stars are more likely to have companions and more of them.
And among these higher order systems, you mentioned triples.
Triples truly reign supreme. Systems with 4 or more components are far less common. For some historical context, we look back at a comprehensive catalog from 1999 by Tocqueville.
Okay.
Out of 728 higher multiplicity systems cataloged then, 551 of them were triples. So it really emphasizes their dominance among the multiples.
Still, finding them must have been hard back then.
Oh, incredibly challenging. Getting a complete census of these complex systems was, for a long time, really difficult. Past studies, like one in 2010 focusing on solar-type stars within just 25 parsecs, only identified about 56 systems.
It's not many.
Not at all. And these efforts were often hampered by strong selection effects,
Meaning?
meaning our telescopes and methods could only easily see certain types of systems, which biased the results. And there was non-uniform coverage of the full range of parameters like orbital periods and mass ratios. It was like trying to understand a whole forest by only looking at, the trees right by the path.
Okay, so we had glimpses, but not the whole picture.
Right. But we did get a pretty good pre-Gaia snapshot from the Hipparcos mission. For F and G dwarf stars, kind of like our sun, within 67 parsecs, a sample included nearly 5,000 primary stars. They found about 2,200 known stellar pairs. Among those, 361 systems range from triples all the way up to quintuples 5 stars.
5 stars bound together. Amazing.
It is. And that particular analysis, this was Tocqueville again in 2014, found an overall multiplicity rate of 46% for systems with 2 or more components.
46%, so almost half.
Almost half, yeah. The breakdown was quite telling. 54% single stars, 33% binary, 8% triple, 4% quadruple, and just 1% quintuple.
So even before Gaia, the picture was clear, while single stars were still the majority.
Just barely. A surprisingly significant 46% of stars lived with companions. This already challenged our traditional view, showing a surprisingly, social cosmic neighborhood. Binaries, triples, even more complex systems were more common than often assumed.
Which brings us, inevitably, to Gaia, this European Space Agency observatory. It's just given us this unprecedented, incredibly precise astrometric and photometric census of our galaxy. It's truly revolutionary, isn't it?
Absolutely game-changing.
Yeah.
But what's interesting is that the early Gaia binary compilations, like the million-star binary catalog from El Badri and colleagues in 2021, using early data,
Yeah.
they actually removed triple systems from their list.
Remove them. Why would they do that?
Because identifying triple systems with statistical certainty is far more complex. It requires incredibly precise and long-term astrometric data. It's like trying to untangle 3 dancing partners just from their combined shadow. It's very, very tricky. The models get much harder.
Ah, okay. So they simplified things initially.
Right. But this is where the breakthrough comes in. A specific effort was made, again by Tocqueville in 2022, to identify triples that Gaia could resolve.
How?
By starting with the Gaia catalog of nearby stars, focusing within 100 parsecs, he used common proper motions, essentially looking for stars that are visibly moving across the sky together, like a coherent dance team. If they move together, it indicates they are gravitationally bound.
Clever.
Yeah. And with this technique, he was able to identify 392 hierarchical triple systems, along with 30 quadruples and even 1 quintuple system called Eta Scorpii.
So a dedicated search paid off. And this sample must be pretty unbiased, right, given Gaia's coverage?
Exactly. Given its uniform selection criteria and sheer size, this sample provides an unprecedented, unbiased census of wide triples, at least the ones Gaia can resolve. And Tocqueville's work revealed some really interesting insights.
Like what?
For instance, the median primary mass of these triples is about 0.71 solar masses, and notably, all components in these systems are more massive than the average field star.
So confirming that idea about mass and multiplicity.
It certainly suggests a preference for more massive stars to have these complex families.
Now what about the separations? How spread out are they?
Also quite striking. The median inner separation is about 151 astronomical units AU. For context, that's like 5 times the distance from our sun out to Neptune.
Whoa, okay. And the outer.
The median outer separation stretches to around 2570 AU. That's huge, nearly 65 times the Neptune distance.
Wow.
And the median ratio between those inner and outer separations is about 14.7, which suggests that many of these wide triples are sitting just above their dynamical stability limit.
Meaning they're barely holding together.
Pretty much, yeah. right on the edge of gravitational chaos, where even a slight nudge could potentially tear them apart over cosmic time.
Okay, that's fascinating. What about how they're oriented? Are the inner and outer orbits lined up?
That's another interesting finding. It turns out the inner and outer orbits are almost randomly aligned. The average mutual inclination is about 83 degrees.
So picture two hula hoops, one inside the other, spinning at really different angles.
Exactly. Not lined up at all, on average. And when it comes to eccentricity, how stretched out an orbit is, the mean inner eccentricity is about 0.66. This resembles what we call a thermal distribution.
Thermal, like heat.
Sort of. It means their orbits varied widely in how stretched out or circular they were, much like the random motion of gas particles in a hot system. It suggests a kind of natural, unforced state.
Okay, but the outer orbit.
The mean outer eccentricity is smaller, around 0.54. This suggests that dynamical instabilities, that chaos we mentioned, have actually kicked out some of the more eccentric outer orbits over time, leaving only the more stable, slightly less eccentric ones behind.
The system sort of settles itself down over time.
In a way, yes. But
Hmm.
it's important to remember, while this resolved sample from Gaia is incredible, it's only a small fraction of all such hierarchical systems out there.
Right, the tip of the iceberg.
Definitely. Many inner pairs are simply too close together for even Gaia to resolve they appear as a single point of light. But their existence can sometimes be inferred from increased astrometric noise, a subtle, unexplained jiggling in the star's measured position, or from variable radial velocities detected spectroscopically. Kokobedin actually estimated that the total number of triple systems just within 100 parsecs could be around 10,000.
10,000. Compared to the few hundred directly resolved, that's a huge hidden population.
It really is. And the census continues to expand. Tokovinen in 2023 produced an even larger list, 8,000 candidate multiples derived from wide binaries found in the Gaia catalog of nearby stars.
Candidates based on that noise.
Exactly. Many of these candidates showed that excessive astrometric noise, strongly suggesting hidden inner subsystems. And follow-up observations are key. For instance, using the SR telescope in the southern hemisphere, astronomers looked at over 1,200 southern candidates and resolved over 500 new pairs.
Wow, so ground-based telescopes are still crucial.
Absolutely. When combined with other existing ground-based data, this brings the total number of known nearby hierarchical systems up to an impressive 2,754. It's like we're peeling back layers of an onion, revealing more and more complexity.
So, after all these incredible findings and complex data, let's circle back. What's the big picture here? Why does characterizing these intricate stellar systems matter so profoundly?
Yeah, good question. It all comes back to understanding the underlying processes of star formation itself.
The nursery conditions again.
Right. By meticulously characterizing these complex systems, their masses, orbits, alignments, we gain crucial data points to differentiate between those two primary theories we discussed earlier: core fragmentation versus gravitationally unstable disk accretion.
Because each theory predicts different outcomes.
Exactly. Each theory predicts different properties for the multiple systems. It forms different distributions of periods, mass ratios, eccentricities, so observing them closely helps us validate or challenge those models.
Indeed. And one really specific puzzle this helps with is the formation of very close binaries, right?
Yes, that's a big one. We see binary stars where their orbits seem to have shrunk massively, by
Oh.
factors of 10 to 100 since they first formed.
Trunked. How close are we talking?
We're talking about main sequence stars, like our Sun, having companions just a few stellar radii away. That's far, far closer than our standard star formation models typically predict they should form.
And these really tight pairs often have a third star further out.
Often, yes. These compact binaries frequently have a more distant tertiary companion, and their overall characteristics are notably distinct from the general binary population.
Which suggests something special happened to them.
Exactly. And this has led to the suggestion that their extreme closeness might be linked to a rather non-intuitive effect called the Kozai-Lidov resonance mechanism.
Kozai-Lidov. Okay, I've heard of that. It sounds almost counterintuitive. How can a distant companion make an inner orbit shrink? Can you help us visualize that cosmic dance?
Sure, let's try. It was discovered independently by Kozai in 1962, looking at asteroids, and Lidov in 1962, looking at artificial satellites.
Okay.
Think of it like this. You have an inner binary and a distant third star orbiting it. If the inner binary orbit starts out relatively circular, but it's tilted at a critical angle relative to the outer star's orbit.
Tilted.
Right, like
This
a-
hula hoop.
Exactly. If the inclination is just right, typically above about 40 degrees, the gravitational pull from the outer star causes the inner binary's orbit to oscillate periodically. It swings between being very circular but highly inclined to being highly eccentric, very stretched out.
Back and forth.
Precisely. And during that high eccentricity phase, the two inner stars can get incredibly close to each other at their point of closest approach. So close that tidal forces between them, or maybe interactions with disks, can dissipate orbital energy.
And that shrinks and circularizes the orbit.
That's the idea. It shrinks the orbit permanently, leaving behind that very tight binary we observe today.
Wow. Okay, that makes a kind of weird sense.
It does. And it's not just stars. This mechanism is also believed to operate for some exoplanet orbits. It might explain some of the incredibly eccentric planetary orbits we see, and maybe even help form hot Jupiters, those gas giants orbiting scorchingly close to their stars.
Fascinating. But is it the whole story for close binaries?
Well, that's where things get interesting again. New findings from Huang in 2023, using Gaia DR3 data, are challenging some of these assumptions, at least for certain systems.
Oh, what did Huang find?
Huang specifically looked for resolved tertiary companions, but ones at vast separations, from about 1,000 up to 10,000 AU orbiting known close binary systems.
So really wide tertiaries around tight inner pairs.
Exactly. And what they found was surprising. The fraction of systems having these wide tertiaries actually increases as the orbital period of the inner binary decreases.
Wait, so the closer the inner pair, the more likely they are to have a really distant third wheel? That seems backward if Kozai-Lidov needs that third star.
It does seem a bit counterintuitive for that specific mechanism, doesn't it? And here's the crucial point. The inferred eccentricities of these wide tertiaries were consistent with that thermal distribution we talked about earlier, similar to wide binaries that don't have close inner pairs.
Meaning their orbits look kind of random, not necessarily shaped by some dramatic Kozai-Lidov process.
That's the implication. This appears to exclude the Kozai-Lidov mechanism as the primary explanation for most of these specific wide tertiaries, at least the ones out beyond 1,000 AU.
So Kozai-Lidov might still work for closer tertiaries, but not these super wide ones?
Exactly. This isn't to say Kozai-Lidov doesn't happen at all. It almost certainly does in some cases. But for these specific wide tertiary systems around close binaries, it challenges that long-held belief. It means we might need other explanations for how some of these complex systems form and evolve. Maybe the inner pair formed tight initially, or something else happened.
Always more questions.
Always. But Gaia is giving us the data to ask them more precisely. And to give you a more tangible feel for these discoveries, Gaia data is illuminating some truly fascinating specific examples.
Oh yeah, like what?
Take the first resolved triple white dwarf system ever found, named J1953, dato 019.
Triple white dwarf. So 3 dead stars.
3 stellar remnants, yeah. What's left after stars like our sun, or a bit more massive, die. This was discovered using Gaia DR2, combined with other survey data. And the cool thing is all 3 members have pure hydrogen atmospheres. Their masses are all very similar, between 0.60 and 0.63 solar masses. And their cooling ages are all consistent with them having evolved and died around the same time, between 40 and 290 million years ago.
Wow, it's like finding a perfectly preserved, co-evolving family portrait right at the end of their stellar lives.
That's a perfect analogy. And we've even found quintuple systems, 5 stars bound together.
You mentioned one earlier, Scorpii. Are there others nearby?
Yes, the nearest known ones are GJ644, just 6.4 parsecs away, and Epsilon Ursae Majoris, that's actually a star in the Big Dipper, at 8.3 parsecs.
In the Big Dipper, I had no idea.
Yeah, and Tokovinen, back in 2020, derived detailed properties for 2 others, Sigma Tucana and Eta Scorpio, both systems hosted by solar-type stars. Their properties, particularly the strongly correlated masses of the components and their wide orbits, strongly suggest they formed by fragmentation in relative isolation.
Fragmentation.
Meaning all the components likely accreted gas from a common source, a shared envelope, during their formation. It points towards a process called hierarchical collapse, where the larger cosmic cloud breaks down into smaller bound systems over time, almost like an intricate fractal pattern.
It's just a breathtaking look into the cosmic nurseries where stars are born, isn't it? Showing us that these complex families are not just common, but incredibly diverse in their structures and how they evolved.
Absolutely.
So we've really journeyed from that basic concept of stars having companions, dug into the intricate details of triple system dynamics, saw their profound implications for figuring out how stars actually form, and even how existing theories like Kozai-Lidov are being refined and challenged by this amazing new data.
It's truly a testament to the power of precise observation, especially what Gaia is achieving.
And the promise of Gaia is far from over, right? There's more data coming.
Oh yes, future Gaia data releases will continue to enrich this 100 parsec triple star sample, adding even more close-resolved binaries and providing crucial astrometric and spectroscopic orbits for countless more systems. Each new data point is another piece of this giant cosmic puzzle.
So, a final thought for everyone listening. When you next gaze up at the night sky, just consider this. Most of those twinkling lights are likely not alone. They're part of complex, dancing stellar families locked in these intricate gravitational embraces. What new secrets about our universe will Gaia reveal next as it continues to map these celestial ballets, showing us the true, often hidden social lives of stars?